So we talked about 5 types of thinking errors. They're all related, and they all relate to those tricky conditional objective probabilities that we started out talking about. And perhaps you're a bit dejected. And one of the people asking a question during the break, basically concluded that isn't it weird that we test our hypotheses this way? Isn't it not that informative that if we think such and such is the case, that we assume that if there's actually nothing going on, how likely would this result then be? And especially given that that whole procedure is so sensitive to the individual decisions of the researcher and the intentions of the researchers as well. So isn't that a weird way of going about testing our statistical hypotheses? And if you're inclined to think that, there are people that agree with you. So there are people that would like you to invite you to think about Bayesian alternatives to the stuff we've been talking about so far. The point for the final part of this lecture is twofold. First of all, I want to introduce you to that Bayesian alternative, basically by pointing out a couple of the things that we've already been talking about so far. So it's all related to that formula for conditional probabilities, which you can also call Bayes' theorem, which is the basis of Bayesian statistics, which is all the stuff about conditional probabilities we've been talking about so far. And the second point is to give you a gentle introduction, or to make sure that when you enter the lecture hall with Sharon next week, and the week after that with Danny and Erik Jan, when they're going to debate the difference between null hypothesis testing and Bayesian analysis, that you have an intuitive understanding of what we're talking about and how the two approaches are different. So I'm laying the groundwork for the stuff next week and the week after that. All right, so basically what you're trying to do when performing a Bayesian data analysis is updating your beliefs, and updating your beliefs in a way that accords with rules of probability. Perhaps you remember that that's one of the benchmarks of rationality that we talked about in the second lecture, right? I said, can human beings be considered to be rational? And I gave 3 criteria that we could use. And the second one was, do we update our degree of belief in accordance with rules of probability? And most people don't. And you could say that Bayesian reasoning is making sure that you do update your beliefs given new evidence following the rules of probability. Basically, it's applying that conditional probability formula that we've been talking about so much so far, and use it to combine your prior beliefs, so what you initially believed to be true about the world, and new evidence that you've gathered, and combine them, and in so doing produce updated beliefs about the world. You can do that magically by using Bayes' theorem, which is the formula depicted in the arrow. And I'm not going to talk about detailed how-to guides for doing analysis and interpreting the results. I'm going to talk about what this process means, and I hope that after this part of the lecture you have a more intuitive feeling for what you're doing when you end up doing Bayesian analysis. Basically what you're doing when doing Bayesian analysis, or when you're thinking like a Bayesian, is reallocating credibility across possibilities. So we're talking here about degree of belief, right? So we're not talking about those objective probabilities. Now we're back to talking subjective probabilities. Another way of talking about subjective probabilities is saying that we're talking about degree of belief, the degree to which we believe something to be the case. And we reallocating this. We're basically saying, well, before gathering data, we think that all options are just as likely. So one way of making this explicit is the following. Let's say you're playing Cluedo, and there are 3 suspects, right? In Cluedo, perhaps you remember, you need to decide who is the murderer in a murder case, and there are different suspects. And in this case, we have 3 different suspects. There's Dominee Groenewoud, Reverend Greenwood, Professor Pimple, and Rosa Roodhart, Rosa Redhart in Dutch. These are 3 cards. And let's say before you get started, your degree of belief that any of these is the actual murderer is equal, right? So your credibility, so the possibilities is either this person is the murderer, this person is the murderer, that person is the murderer. Those are the 3 possibilities. And the height of the card in this case indicates the degree or credibility in each of these possibilities. So the degree to which we believe that one person is the murderer over the other. And what you can see is that our degree of belief that any one of these is the murderer is equal. right? So we're undecided, and we don't suspect the one person over the other. And what we're doing with Bayesian analysis is reallocating that credibility, right? Reallocating that degree of belief. So after gathering more data, so you find a murder rapper, for example, your degree of belief might look like this. So you suspect to a larger degree that Rosa is the murderer, and you suspect to a lesser degree that the reverend is the murderer. And that's basically what we're doing, right? We're getting from here this allocation of credibility to this allocation of credibility, which reflects the fact that after gathering data, we think it's more likely that Rosa is the killer than the other two people are the killers. It could also look like this, right? So we found new evidence, and we think the first two persons are more likely to be the killer, and it became much less relevant that the final person was the killer. So I'm basically showing you these graphics because this is the only way I know how to give a visual image of what we're doing. We're having a degree of belief, we're undecided between different possibilities, and the allocation of the degree of belief, of the credibility, changes over the course of gathering data, which is what we're doing with Bayesian analysis. So we're getting from our prior convictions to posterior beliefs through applying Bayes' theorem depicted in the arrow. So that's basically it, right? Well, let's say we have prior convictions. As I said, we're undecided who might be the killer, and we think it's equally likely that any one of these three persons is the killer, which is indeed the prior in the formula we're talking about, right? And that's the beauty of Bayes, right? Because we talked about people inversing conditional probabilities when testing null hypotheses, and we're saying, well, you can't actually go about inversing conditional probabilities because we don't have a Bayes rate. And because we switch to subjective probabilities, we do have that Bayes rate, which is called the prior in Bayesian analysis. And we do have a substantive interpretation for that prior, which is our belief or the allocation of our credibility over different possibilities before we did research, which is depicted here, and we're undecided between the three cases. And then we add the likelihood, which is this part of the formula. And the likelihood depicts the likelihood of finding specific data given that a specific hypothesis is true in this instance. So our hypotheses here are the different possibilities, right? So either this is the murderer, this is the murderer, or this is the murderer. And our data is the fact that we found a bloody bow tie, right? That's one of the clues that we found in Cluedo. So you go around looking, you see, oh, there's a hint, right? I found a bloody bow tie. And then you think, well, how likely is it for me to find a bloody bow tie given that the Reverend is the murderer, or given that Professor Pimple is the murderer, and given that Rosa is the murderer? So you're actually indicating how credible or how predictive are my different hypotheses of the data. How likely am I to find a bloody bow tie given that the Reverend is the murderer? How likely am I to find it given that Pimple is the murderer, or given that Rosa is the murderer? And you would agree with me that given that Professor Pimple, here he is, wearing a bow tie, and he always wears a bow tie and the other two don't, makes it more likely that we find, so if we don't know whether he's the murderer, but if Professor Pimple were the murderer, it would be more likely for us to find a bloody bow tie than if any of the others were the murderer, right? That's basically what we're checking here, which is what we call the likelihood. How likely is the data, the bloody bow tie, to occur given a specific hypothesis? And then we do something else. We can add the marginal probability, and I will cover that in more detail perhaps at the end of the lecture. It's not that essential for your understanding here. But you basically look at the probability of the data. So how likely is it to find the bloody bow tie at all, given all different possibilities? So how likely are you to find it given that this person is the murderer, this person is the murderer, and this person is the murderer? And then what you can do is compare, or you can keep it in general terms. So what you can do is update your beliefs, right? We started out with a prior belief in which we, to an equal degree, believed that any one of these could be the murderer. And we looked at the likelihood. So we found evidence, we've collected new data, and we've looked at how predictive are these different models, these different hypotheses. these different suspects of finding that data. How likely are we to find that specific piece of information, the bloody bow tie, given that any one of these is the perpetrator? And we use that in updating our beliefs and coming up with a posterior distribution of credibility. And that's basically, hopefully in an intuitive way, how we update our prior beliefs to posterior beliefs using Bayesian analysis. We collect data, we found a bloody bow tie, and we've looked at how predictive is each of these hypotheses for finding this data, what's the likelihood, and we've used that to update our priors and get to our posterior beliefs. So, if we're talking about Bayesian inference being reallocation of credibility across possibilities, you now know you can make it more specific. With credibility, we mean subjective probability or degree of belief, right? That's subjective probability we talked about in the beginning of the lecture. And the possibilities are those parameter values, right? So we look at, with likelihood, we look at how predictive those different parameter values are for the data that we've actually found. We use that for coming up with our posterior. So the degree of belief we should have in different parameter values are accurate given the data that we found. For now, I hope you understand intuitively that this is what we're doing. We're moving around the degree to which we believe something to be true on the basis of the data that we found, and we do that by plugging it into Bayes' theorem. That's basically what you're doing with Bayesian analysis, reallocating credibility across possibilities. And then you might wonder, how do you do that? So what happens when you plug those values into the Bayes' theorem? And that's the final part of this lecture. I want you to give you a more intuitive sense of what those different aspects of Bayes' theorem actually mean in the context of Bayesian data analysis. First of all, the likelihood, right? So we've already talked about this a bit. I'm sorry, my mouse is malfunctioning a bit. All right. So what is the likelihood? I already tried to point that out, but we could make it more specific and use actual numbers, but with an easy example. So we've talked about different possibilities, right? And allocating credibility across possibilities, and those possibilities are parameter values. Those are different models that you could use, and you could check how predictive these models are, and that's what you call the likelihood. So let's say we have a specific value for theta, or assumed parameter value for theta, and it's related to an experiment in which we gather data on the following. So there's a gate somewhere near where I live, and let's say behind this gate is the population I'm interested in, and random individuals out of that population would walk through this gate at any given time. And what I'm interested in is the proportion of people that shout tequila when they walk through that gate. Right, so you know the song, it goes on forever, and then at the end somebody shouts tequila. And there's also always a difference in parties, right? People that shout tequila at the end of the song and people who don't. And perhaps that's what you're interested in, right? There's two types of people. They either shout tequila or not. And we can make assumptions about what proportion of people in the population are actually tequila shouters. And for this example, we've assumed that actually 10% of people, or 0.1, of the people are tequila shouters. And let's say we collect some data. So we check for the first 5 persons randomly selected to walk through that gate, and we check whether they shout tequila or not. And it turns out all 5 of them shout tequila, right? That's our data. So what we then can calculate is our likelihood. How likely is the data of having 5 tequila shouters in a row, given that the actual population parameter is 0.1, right? So given that 10% of all the people in the population are tequila shouters, how likely is it for this data to occur? How likely is it for the first 5 persons to walk through this gate to be shouting tequila? And that's something you can calculate, and that's just a basic probability theory, right? So that's that the 0.1 times 0.1 times 0.1 times 0.1 times 0.1 gives you that specific probability. And then So that you should be able to follow. So how likely is the first person to be a tequila shouter? That's 0.1, and how likely is an additional person? That's this time 0.1 times 0.1, and so forth until you get to 5. But you can do that with different probabilities. You can also say, well, the probability or the proportion of tequila shouters in the population is 0.2. It's not 0.1, and you can again calculate a likelihood for that. So how likely is the data, the same data, 5 people through the gate are tequila shouters, given that the proportion in population is 0.2, or given that it's 0.3, and given that it's 0.5, right? And you can make a graph of that, depicting the likelihood for different parameter values, given that the actual proportion is 0.1, 0.2, 0.3, 0.4, 0.5, etc. How likely is it that the first 5 persons walking through that gate will shout tequila? This is the first step to understanding what a likelihood function actually indicates. And I've done this with discrete values, right? I've assumed 9 different values for the population parameter, and I've calculated how likely the data is given that the actual proportion is such and such. And I did that with different specific values, and I've plugged those into a histogram, and then you get a semblance of what a likelihood function is. It's a semblance because the likelihood functions you're going to talk about in the lecture with Sharon and in the debates and when you're actually going to perform Bayesian data analysis yourself are continuous. So the different parameter values and the likelihood across the different parameter values that we're graphing is continuous as well. So it's not a bunch of bars, but it's more of a continuous distribution. But I've taken these steps with a simple calculation to a bunch of calculations, and in the infinite run, that's how you can imagine or can construct your thinking about likelihood functions. You would end up with a likelihood function, a continuous distribution of the likelihood across different parameter values. All right. So we've looked at the likelihood, which is a crucial ingredient of Bayesian data analysis. Right, so we're talking, it should be clear to you that with the likelihood we mean the probability of this data given a hypothesis, a specific, and the hypotheses are per a specific parameter value. And we've talked about the idea that the likelihood function gives a distribution of the likelihood over the full range of possible parameter values. So we've given a couple of discrete parameter values. And if you just imagine that we fill in all the gaps between 0.8 and 0.9, 0.7 and 0.8, then you get a more continuous distribution, and that's what we call the likelihood function. So you know what a likelihood is, and you know what a likelihood function is, so you properly understand that part of Bayes' theorem. And we're talking about what you can do with your data in a Bayesian analysis, right? So what we're basically checking is how predictive is one specific parameter value for the data to occur. So how predictive is a parameter value of 0.1 for the fact that the first 5 people through the door shouted tequila, right? That's the likelihood. We're looking at how predictive is the model of the data. One way you can do that is by calculating a likelihood. Another way you can do that is by calculating a Bayes factor. And what you're doing in a Bayes factor is that you're comparing 2 specific parameters. One way in which you can calculate Bayes factor is by comparing 2 specific parameter values. You're actually saying how much more likely is the data to occur given one specific model, one assumption about the population parameter, compared to another assumption about the population parameter. That is actually what we did in the example about Shinkins living in Amsterdam, right? What I actually said is how likely somebody to live in Amsterdam given that he is Dutch, compared to how likely is somebody to live in Amsterdam given that he isn't Dutch. What we actually did was intuitively calculate a Bayes factor there. And what you actually can do by comparing likelihoods in this way, right? We have 2 different likelihoods, one given one assumption about the population parameter and one given another assumption about the population parameter, is that we can actually talk about evidence in a useful way, right? So we can say that, well, that data is more likely to occur given that this parameter value is true compared to another parameter value. So we found evidence in the data for one hypothesis over another hypothesis. And that's a very useful direct comparison, right? Because the issues we've been talking about so far quantifying evidence against the null hypothesis, for example, or finding evidence for the null hypothesis being true, that would require this type of comparisons. So talking about the likelihood of the data given one assumption compared to another assumption. And this is what the Bayes factor allows us to do. So making this type of comparison, plugging it into, using that likelihood and plug it into a Bayes factor could be a useful way of testing hypotheses, which is something that you're going to pick up with Sharon in the next lecture as well. All right, so we've talked about what we do with the data, right? So we've talked about the likelihood, and we've seen how the likelihood is related to the Bayes factor, which are both aspects of what we do with the data and Bayesian analysis, is thinking about how predictive is a specific model of the data that we found, and either making a direct comparison between two different models or between a specific hypothesis or parameter value and a more general range of parameter values. What we still need to talk about is that prior. So to get to that posterior belief, so the degree to which you believe the hypothesis to be true or a specific parameter value to be likely given the data that you found, depends on not only that likelihood, but also on the prior as well. And the prior is, as I already mentioned, the Bayesian's answer, if you will, to the Bayes rate that was lacking in the null hypothesis significant testing approach, right? We talked a lot about the Bayes rate not being there, right? The Bayes rate was absent. I had a tumbleweed going on here. We don't know what the a priori likelihood of the null is because it doesn't have a long-term frequency, right? And that's the reason why I said, well, you can't talk about the Bayes rate of the null hypothesis because we're talking about objective probabilities. Now we're talking about subjective probabilities. So we are allowed to talk about priors. And priors are the degree to which we believe something to be the case before we started doing the analysis. That could be just a general hunch. It could also be on the basis of prior research. It could also be let's call it a neutral prior that somebody else has provided for you that you plug in into your model. But anyway, if we compare it to the frequency tree that we've been using so far, and I've been saying that, well, we don't have a Bayes rate, basically now we do. We have priors and we can formulate priors because they reflect our degree of belief before doing the experiment. And we can use that in that Bayesian theorem, Bayes theorem, and update that belief with the likelihood to get to the posterior distribution. Basically, if we relate that to the tequila example, and this should also sound familiar based on the Cluedo stuff we've talked about, right? So you could think about, again, we're talking about the distribution of credibility across possibilities, and this is the unknown proportion reflects to the unknown proportion of how many people in the population, what proportion of people in the population are tequila shouters. And let's say before doing the experiment, we don't know, right? We're completely blank on that information. And then we can use a flat prior. This prior is completely flat because it reflects the fact that we consider each possible proportion in the population to be equally likely, right? 0.6 is equally likely to 0.2 or 0.0 or 0.8. That's what a flat prior reflects. And that reflects our ignorance, if you will, about the true proportion in the population. That's one assumption that you could make. And if I say I have no idea, that would look like a flat prior. What I'm basically saying, my prior knowledge doesn't allow me to favor one hypothesis over another, and that's reflected in this prior distribution. It could also be the case that I have a somewhat strong conviction that 0.2 is the true population parameter of tequila shouters in the population, right? Perhaps on the basis of prior research or what have you. And then my prior distribution would be more likely to look like this. It would peak above the 0.2 value because I think that to be the most likely population parameter given what I know so far. So this prior distribution reflects my belief that I think 0.2 is the most likely parameter value. And then I would use this instead of the flat prior when doing the rest of my analysis. Could also be the case that I think, well, the proportion of tequila shouters is 0.5. And another thing, so that's one thing that you should know about prior distributions, that the peak of the prior distribution indicates the value that you deem to be most likely to be true about the population before starting your collecting your own research. The other thing is that how narrow or broad the distribution is around that highest point reflects your certainty, right? So if we compare different distributions around 0.5, this one is somewhat broader than this one, which is again somewhat broader than this one. So this is a very narrow distribution around the proportion of 0.5, which indicates that my prior belief is very strong, that the true population parameter is 0.5, right? So I don't consider any alternative proportions to be likely to be true, given all that I know so far. So what I've tried to show you is that what we can do in Bayesian analysis, what we can't do in null hypothesis significant testing or frequent test analyses, is come up with a base rate, which we call priors, which reflect our prior beliefs or prior degree of belief that we expect something to be likely to be true in the population. And that is reflected in the prior distribution, which can show you basic ignorance. I consider all possible values to be equally likely to be true, or I favor one specific proportion over another, and to the degree that the prior distribution becomes narrower, that reflects a stronger degree of belief that that is the true population parameter. So we've looked we've looked intuitively at two concepts, the likelihood and the prior, and you should have an intuitive sense of what we mean by that and how we use it for doing that data analysis, how we plug it into that Bayes theorem formula. If you want to play around with those priors and you want to change it around a bit, you can click on this link and you go to a Shiny app, which, is self-explanatory basically. It's very similar to the stuff I've been talking about, only it doesn't talk about tequila shouters, but it talks about a bag of candies, which are either yellow or red or something, two colors, and you can pull candy out of the bag at random, and what's then the probability given your prior beliefs about the distribution of candy in the bag, etc., etc., etc. And you can change around, you can play around with the priors, and what you can also do is look at what different priors have. So if you combine the prior and the likelihood, what impact that has on your posterior distribution. So what you basically need to remember from what I've just told you is that we've looked at the formula for conditional probabilities and we applied that to data analysis. We've looked at how probable is a certain hypothesis to be true, or what should our degree of belief be that one parameter value is the correct one given the data, and we can calculate that by using the likelihood and the prior. And you should know what the likelihood and the prior reflect and how they're related to distributions. We can, and I will shortly talk about the marginal likelihood, but as you're going to see in the chapter by Dinas that you're going to read next week, we can also ignore that for the time being. And we're not talking about this equals that, but we're saying that this is proportional to the likelihood times prior. So the degree to which this goes up or down or changes is proportional to the degree that this goes up or down or changes. Which is a beautiful thing. I don't necessarily want you to become Bayesian in your data analysis, but this reflects a very intuitive way in which we like to think about data and evidence, right? Because basically what this says is that our change in the degree of belief that we think that one thing is true is proportionally related to the amount of evidence that we found combined with our prior convictions that something was to be the case. And that's consider that, right? Let that sink in. I think that's beautiful. We're basically saying, in very simple terms, you had prior convictions about the world, we've added evidence, and the combination of those two should determine your posterior beliefs that something is the case. And that's what we're using Bayes' theorem for formalizing that step in your reasoning. So basically, if you apply that to the different Cluedo suspects, what we're saying is that my degree of belief that Professor Pimple is the killer, given that we found a bloody bow tie, so the degree of belief that a specific parameter value holds, a specific suspect is the murderer, given that we found certain evidence. So the degree of belief that Pimple is the killer given that we found a bloody bow tie is proportional to the probability of finding a bloody bow tie given that Pimple is the killer. How predictive is the assumption that Pimple is indeed the killer for us finding a bloody bow tie, and our prior conviction that he was indeed the killer? That's intuitive, right? So I have a degree of belief that somebody is a perpetrator. I find evidence, so I found new material, and I consider how predictive different assumptions are. How predictive would the assumption that someone is the killer be for finding that evidence? I combine the two, and then I get my degree of belief, or that changes my degree of belief proportionally that somebody must be the killer. So finally, and very shortly, because I don't think this is essential for you understanding Bayes. So everything I talked about so far is essential for you understanding Bayes. The fact that these two are proportional, right? That the posterior is proportional to likelihood times prior. That's important. But perhaps some of you were wondering what's happening here, right? What is the probability of the data? And we call that the marginal likelihood. And I want to end this lecture by giving you briefly an intuition for what that reflects. Basically, if we talk about put into a frequency tree the possible perpetrators, let's say Pimple is a perpetrator or somebody else is, then there's a probability of us finding the bloody bow tie, but there's also a probability of us finding the bloody bow tie if somebody else than Pimple is the murderer. And basically, what we're talking about when we're talking about the probability of the evidence is the probability of us finding the bloody bow tie, irrespective of who we assume the murderer to be. So how likely is to find the bloody bow tie given that somebody else is the murderer, plus how likely is it for us to find the bloody bow tie given that Pimple is the murderer, and that gives us that marginal likelihood. Basically, what that makes this equation for us is a simple ratio, right? So actually what we're saying is that how likely are we to find this evidence given that Pimple is the murderer, combined with our prior conviction that Pimple is the murderer, and we compare that with a general prediction. So if we take an average of the probability of finding the same evidence, the bloody bow tie, given that anybody else would be the murderer, or the average person would be the murderer, or the average suspect would be the murderer, that's the comparison we're making. So how much more predictive of the data is this assumption over any other assumptions that we could make? That's basically what we're trying to do by using Bayes' theorem in Bayesian data analysis. Again, you don't necessarily have to understand that marginal likelihood, but I wanted to give you a...
Can you repeat the last sentence? Because...
Right. Yeah. So what we're basically saying is how much more predictive or better predictive one specific assumption is, let's say Pimple is the murderer, over a general prediction that you could make on different, all other different parameter values. Yeah, that's basically it.
Okay, thanks.
Yeah. So if you would make that into a beautiful picture, at least I spent some time on that. This is basically what you're saying. So how much more likely are we to find the bloody bow tie given that Pimple is the murderer, compared to how likely are we to find the bloody bow tie irrespective of who is the murderer, given that either the Reverend or Rosa or Pimple is the murderer. That's basically what we're comparing here. All right. And again, in a Bayesian analysis, you could go for a Bayes factor, and then basically what you're saying is how much more predictive would the assumption that Pimple is the murderer be for finding a bow tie compared to a specific alternative, given that the Reverend is the actual murderer.
Ask a question again really quick about that.
Yeah,
about
sure.
The PD. So is the PD basically kind of like the type 1 error then?
No.
No.
If you relate it to that, so if you compare that with null hypothesis testing, the type 1 error would be rejecting the null if there's no real effect, and the probability of the data would be what is the probability of rejecting the null hypothesis, and that could either be in this case or in that case. So that's different from the type 1 error rate.
Okay. Yeah.
Would be my intuitive answer, and we can talk about it somewhat longer if you'd like after the lecture. If you were confused by that, forget about it. It's a very good question, by the way. But I just I want to point out that it's not in that way related to the type 1 error probability. Okay, so summarizing, what I've tried to show you today is how null hypothesis significance testing can go wrong. So we overly focused on p-values and whether they're significant or below an alpha level. We're very ritualistic in our approach to null hypothesis testing in that way. So we assume alpha on 0.05 because everyone is doing it, and we tend to neglect power a lot of the times because we think it's not relevant anymore once we've shown an effect or we've rejected the null. And I hope that you better understand by looking into those common thinking errors and by again emphasizing that null hypothesis testing is about objective and conditional probabilities. You better understand why the p-value doesn't show us a probability of a replication, or even given that we have a significant result, it's still relevant to know what the actual power of your test is, and why we can't inverse conditional probabilities because of, Sharknado, but also because the more detailed explanation about what p-values mean and how they reflect conditional probabilities, and we can't just go about inversing them. That raises a bunch of issues, and that might have made you less satisfied about the procedures that we're actually teaching you and how you go about testing your own null hypotheses. And perhaps you're looking out for another alternative that might be considered more intuitive. And I've given you the first glimpse of what that alternative could be. That's that Bayesian data analysis. And I hope that you understand, at least after this lecture, how that connects to everything we've been talking about so far, right? All the steps and the reasoning errors that I've explained, I've related that to that formula for conditional probabilities, which is the centerpiece of that Bayesian analysis, right? They use that conditional probabilities formula for updating their beliefs on the basis of new evidence, which might make more sense to you. But there's a cost-benefit analysis, as there is in everything, right? So we have to let go of objective probabilities and accept that we're using subjective probabilities instead. And that comes at a cost. There's no error rate control, at least not as clearly as in the NHST examples you're familiar with. So it's debatable whether you should prefer the one approach or the other. Or you could think, well, given the specific context of my research question, it's better to use my NHST tools, or it's better to use my Bayesian tools instead, which would be a very beautiful outcome of this course, that you consider all the stuff we're teaching you not as a forced ritual, a mindless ritual, but as a toolbox from which you can pick the tools you need for the problem at